Hello, welcome to an ESTOMAD project demonstrator movie. This movie will present the ESTOMAD approach applied to FMTC's badminton robot. ESTOMAD is a project that developed tools and methodologies for the energetic virtual prototyping of machinery. Sustainability, energy consumption, and the ecological footprint are becoming key factors in future machine design. Therefore, the consortium of the European project ESTOMAD has developed methods and tools that allow to take energy consumption already into account during the design phase of a machine design. The main concept of the badminton robot looks as follows. A badminton racket is connected to a robot arm that allows rotating the racket and hitting with the racket. This robot arm is moved across the field with a linear motor. A system of two cameras that is placed next to the field locates the badminton shuttle. Based on an estimation of the motion of the shuttle, the robot is moved to the right position and hits the shuttle back to the badminton player. And now, let's see the badminton robot in action. We would like to reduce the energy consumption of the robot. To do so, we applied the ESTOMAD approach. The analysis is limited to the linear motor, as this is the main source of losses present in the system. An energetic model of the linear motor has been made, including the mechanics, electronics, and controls. Parameters of these models have been optimized using data obtained from experiments on the robot. Using this model, the energy flows in the robot were analyzed for a typical right-to-left motion. From this analysis, it was concluded that almost half of the energy is consumed by ohmic losses in the motor and friction losses in the guides. The ohmic losses are proportional to the square of the acceleration of the motor, and the friction losses are proportional to the speed of the motor. Therefore, a more efficient robot could be realized by minimizing the acceleration and the velocity of the robot motion. The initial control strategy of the robot was to move as quick as possible to the interception point. As a result, the robot often has to wait until the shuttle arrives at the interception point. This waiting time can be exploited to reduce the acceleration and velocity of the motor. The as quick as possible control strategy should be changed in a just-in-time control strategy. This can be realized by changing the trajectory generator parameters. A multi-objective optimization was used to obtain optimal trajectory generator parameters. The minimal energy that is needed to move the robot over a specified distance in a specified time is calculated. The maximum acceleration and velocity related to this minimal energy trajectory are derived. These parameters are integrated in the controller scheme of the linear motor. Only a software modification is needed to change the as quick as possible control strategy to the just-in-time control strategy. Presented energy flow chart shows the system energetic behavior while the time optimal trajectory parameters are selected. Energy dissipation on different components of the system before and after optimization are shown here, and we can easily observe that the optimization was a success. The energy consumption during standard badminton play reduced with more than 50%. Comparing the behavior of the robot in both controller modes, one can observe that robot behaves in a more relaxed way when the energy optimal controller is implemented. The ESTOMAD approach allowed optimizing the energetic behavior of the badminton robot. A significant reduction of energy consumption of more than 50% could be realized with only software modifications to the robot.